Let's walk through the calorimetry simulation. So here's the link that you're going to use, and we'll pull up this simulation here. We're going to do this simulation 6 times. Let me go back to our procedure here. So we're going to run the same thing, pretty much the same thing 6 times. Here we go. We'll do iron, and we'll have iron at 10 grams, and then you'll switch it up to 25. You'll keep the mass of the water the same, and then in trial 3, you're going to double the mass of the water, go back to the same amount of iron, and figure out how that changes all of these quantities, how much heat's being transferred. Then you'll try a different metal, and then 2 unknowns, and we're going to try to identify these unknowns. So once you figure out what the unknown is, make sure you add that to your abstract and your conclusions. And you'll identify them. You're going to need this table here. We're going to identify these unknowns based on their specific heat capacity. So in this simulation, what we're going to do is just the same thing that we would do if we were in lab. You would take a solid, let's try copper. Since I'm asking you to do iron and aluminum in the lab, we'll do copper. We'll walk through that example here. And we'll drag this little tab over until it says about 10 grams. Good. And initial temperature like 200. And I'm going to record these in Excel because it's if you want to do it in Excel, very, very easy. So we had 10 grams of copper at 200 initial temperature. So this is really hot. So we're going to heat this up. It's going to be really hot. And you can, click that. It'll show you the specific heat capacity here for the known solids. And then you have to click next. And that's going to heat this up. And now we can choose a liquid. We're going to always do water. We'll do 100 grams of water and starting at 20. And record that over here. So 100 grams of water. So here's your water information, 100 grams of water, initial temperature 20. Really, the simulation, all we have to do is try to find the final temperature. So I'm going to take this really, really hot metal. I'm going to drop it into, there we go, into the calorimeter. And you can show this graph. We can watch how the temperature changes for the copper, for the metal, and for the water. And you can kind of see what's going on the microscopic view as well. So our initial temperature was 200 for the metal and 20 for the water. And so what's happening now is all the heat, lots of the heat is coming off of that metal and it's being absorbed by the water. So you can see the water temperature that started at 20 is now going up. Now it's going up to like 21, 22. We'll see where it ends. That's our final temperature. The temperature is going to increase until both of these temperatures are the same. So the water temperature is going to go up and the metal temperature is going to go down. Eventually they're going to equilibrate, and that's where we are right now. So that's at 21.64. So we're going to record that 21.64 as our final temperature for both of these. So they have different initial temperatures. This guy started at 200. It's going to end at 21.64. This one, the water started at 20 and it went up. So the metal is losing heat and the water is absorbing that heat. So to figure out your change in temperature for both of these, you're going to do the final temperature, which is this one. So we have 21.64 minus the initial. And you can see that temperature went down. That makes sense because that's getting colder. The heat is leaving the metal. Over here, my water with my final minus my initial, this went up a little bit. It went up 1.64. Now, the specific heat capacity, if it's a known metal, we can get that right from the simulation. This is copper, so 0.385 down here. You should also be able to find that in the table. It should be pretty close to whatever's in the table here. I have 0.387. That last number could vary depending on your source. So I'll do the one from the simulation, 0.385. And then to find the heat, how much heat is being released here or absorbed, and the metal is releasing the heat. So Q, that's heat, equals mc delta T. So I'm just going to multiply those. I'm going to multiply the mass, which we had 10 grams, times the C, the specific heat capacity, times that change in temperature, this delta T here. So mc delta T. I'm going to do the same thing for the water. Water has a specific heat capacity. There, 4.184. That should also be the same in the simulation, but I don't think I checked the box. Oh, there we go, 4.184. I did check the box. There we go. Here, 4.184. And we can find heat the same way. We have Q is equal to M, mass of the water, M times C times delta T, MC delta T. Boom. So you can see they're pretty close, and that's what we would expect, that the amount of heat that is lost by the metal is being absorbed by the water. So for a known value, we should see that those two numbers are pretty darn close. We will lose a little bit of heat to the calorimeter itself. When we do the unknown, we're just going to assume that all the heat that's lost equals the amount of heat that's gained. It's the opposite amount. If something is gaining heat, the other thing has to be losing heat. So let's try one of our unknown metals. Now in the simulation, we reset this. Make sure you hit that reset button. When we're choosing a solid, if you look at a list of all these solids, we have unknown metal 1, unknown metal 2. Since I asked you to do those in the lab, I'm not going to do that one now. We'll pick a different one. Let's pretend that we don't know that that's tin. We're going to try to, I'm going to show you how you would calculate, how would you determine that that is, the metal. So I'm going to set this to 10, as close to 10 as I can, 10, and initial temperature of 200. So this is an unknown, where we don't know what this is, so I'm not going to click that specific heat button. And then for water, we will set our mass to 100, and our initial temperature is going to be 20. Go to next. If you want to watch the video there, that's fine. So I started at 200 for my metal, and my water is at 20. So I have those temperatures recorded, 10 for my mass, 200 for my temperature, 100 for the mass of the water, 20 for the temperature of the water. And it's going in there. You can see again the metal temperature is going down and the water is going to go up just a little bit. And once they reach the same temperature, once they equilibrate at the same temperature, the temperature is not going to change anymore. So we'll find our final temperature there, 20.93. So we'll record that. Final temperature, 20.93. And also here, 20.93. Now, what I'm going to do is find everything I need to find for water, the amount of heat that's being absorbed by the water, and then I'm going to set that equal to the opposite amount is going to be lost by the metal. And we're going to kind of work backwards to figure out what our specific heat capacity is. So the change in temperature is always going to be the final minus initial. And then Q equals MC delta T. So Q is equal to mass times the specific heat capacity times the change in temperature. Boom. And this will be equal to that, but minus. So if I'm going to, and this is an approximation, this is going to help us figure out what the specific heat capacity is. And then once I figure out the specific heat capacity, I can compare that in the table to figure out what my unknown metal is. So I've got, yep, here we go. So we have let's find our change in temperature, final minus initial, final minus initial. And it's not surprising that that is negative because that's our, temperature's going down. It started off really hot and it lost a lot of heat. So now to find the heat capacity, I use this equation again, Q equals MC delta T, but I'm going to try to solve for the C. So I'm going to divide Q by M in delta T. So I have Q, this Q here, divided by parentheses, make sure you use parentheses, the mass of this metal times the delta T of this metal, there, and I get 0.217. So let's see if that's in our table. Maybe I picked one that's not in the table. I did. So normally that would be in the table, but let's see, we can go back over to our simulation and we'll just click that tin. I think that's what we started with, 0.217. Yeah, so pretty close to that one. So that the ones that you're looking for will be in the table, 0.217. All right, so then based on this, we will compare it to the table and know that our unknown was tin in this case.